Okay, so in this video clip, we're going to take a look at the palmerpenguins R package, which makes available a very interesting data set in R. We're going to set that up and run it in Google Colab. And then we're going to install our tidyverse and then install, of course, the palmerpenguins package, install tidyverse or make the tidyverse suite of commands available in this Google Colab, and then apply these well-known data transformation verbs, mutate, select, filter, summarize, arrange, group by, and a few more standard verbs or grammar for data manipulation. And if you want to get a reference for those verbs to understand or to get some background detail, chapter 5 or for data science is where you might take a look. So we're going to go back then to the Colab, and also we might note that the original data is based on some actual research, and you can take a look at that. You can trace it through here, and the image that we have in terms of where in the globe is the data taken from and where was the research based. It was based in Antarctica, and it's that peninsula archipelago that stretches up into the Falkland Islands, Chile and Argentina. And there is an Anders Island, and then there's 3 additional islands off Anders Island. So we blow it up a little bit here again, and we're getting Dream Island, Turgenson's Island, and Biscoe. And then there's different species of penguin. So the easiest one here is the chinstrap to identify, and the Adelie is in all of them. And this must be the Gentoo penguin, the bigger penguin of the 3. Okay, so let's load in then, run the magic R command so we can activate R in the Google Colab. The native language in Google Colab is Python, but we can execute R. And I'm able to annotate. One of the very nice features here with regard to Colab is you can annotate or document with images and with links and so on, text, what's happening in terms of the Colab. It probably is worth noting that the R package, palmerpenguins, was developed by Allison Horsts, Allison Presmins, and Kristen B. Gorman. And part of their motivation was to get a data set that, if we use this output here, this graph from ggplot2, we can see we have 3 different penguins on 3 different islands, and we can segment then for male, female, and there was a couple that weren't identified. But we see a kind of interesting clustering going on in our data, and we're able to demonstrate that using facet grid from ggplot2. And you sort of get the sense that the actual penguin, we could probably predict the classification in terms of some of the dimensions, so the bill length in millimeters, the flipper length in millimeters, the body mass in grams, and the bill length again in millimeters. If we took these as inputs, we might be able to predict, and using the sex, the size of the classification of the penguin. So if we knew it was female, we knew other characteristics in terms of the numerical data, perhaps we would be able to classify or predict what the penguin species is. And this is a common problem in data science. How do we classify and how do we predict a particular categorization? Maybe in diagnostics and medicine, you want to predict a particular outcome in terms of whether an individual suffers diabetes or not, or a particular type of skin disorder, so on. If you have the numerical data, we might be able to predict whether a particular condition can be accurately signaled in terms of associated attribute data. Okay, so another motivation here for using this data set, the iris data set is probably one of the more celebrated data sets that was developed by Anderson, and the penguin data set is sort of a near replacement. And there's a variety of reasons why you might like to do that. One is just purely to make it attractive, maybe to maybe children, to other types of scientists. Maybe we could frame the discussion in a way that's very interesting. In popular culture, penguins are an animal that attract a lot of attention, a little bit like the pandas. And it's easy to, if you look a little bit here at, in particular, Allison's portal, GitHub, she's developed a lot of artwork. It's really attractive. Do I have some images here? I think I do. This type of imagery, it really is very attractive, and making images that are attractive, that engage people, this also is part of the pedagogic process. So my suspicion is we're going to be working with penguins, and this data set is going to be a fairly significant data set, especially in terms of pedagogy. Okay. Also, there's some serious science going on here. So if you take a look at these links, you can trace back then to the original papers. And, you know, this is very important type of analysis. And the Antarctica, no doubt, with global warming, will be maybe a very significant place in terms of resources, maybe in terms of human population, migration, and so on. So again, if the penguins can survive here, is it possible then that there's food sources, is there protein, and is there the basis then of an area that human beings could settle, right? Okay, so there are many dimensions here. We just touched a couple. Take a look at Allison's links here. They're really nice. And she sets out, if you like, also a set of tidyverse dplyr verbs. And they also are really, really useful in understanding the tidyverse suite. So again, making this analysis attractive, maybe to a different age group, maybe to high school students and so on. This could be part of what's being considered here. And I really like the approach. I really find it attractive. So I think it's worth maybe investing a little bit of time doing something similar myself, right, in terms of setting out and framing a little bit how we could apply these dplyr verbs to the penguin dataset. Now, we've installed the palmerpenguins dataset. That means we can pull in, we can make it available in this environment. So by using this double %R symbol, right, syntax, we can run our code in this Google Colab. Normally Python is the native code in Google Colab, but we can equally run our code. And we've installed, tidyverse comes pre-installed typically in Google Colab. So we just have to enable it by using library, open bracket, tidyverse, close brackets. If we put in, we can sometimes check to see what packages are available in your Colab environment. If you just go into open a cell and put in library open parentheses, close parentheses, you're typically able to find, do you have the ggplots and the other packages, and they normally are there. ggplot2 and dplyr and are normally available. Yeah, so the tidyverse suite is there. Easily install and load the tidyverse, tidyr. Okay, so my sense is they're pre-installed, right? Okay, so we can remove that and come back then to the dplyr verbs, mutate, select, filter, summarize, and arrange. And just a note there, a full discussion of those is also available here, right? Chapter 5 of R for Data Science. There's a full treatment using the NYC Flights 13 dataset, and I have some video explanation of that. If we run the str command, penguins, we get an overview what's in the dataset. If you don't know what str is, we can always query it. Again, if you go into %r and put a question mark and then str and you execute, you can go to the help menu to find out what's in there. And if we just toggle down a little bit, it takes a while, it would appear, we can see that that command compactly displays the internal structure of an R object, a diagnostic function, and an alternative to summary, and to some extent dpyt, right? So again, if you want to, sometimes if there's something you want to actually look at maybe a little bit in detail, one way of getting an overview of the data set is to use the str structure function. And then we can see we have 8 columns, 344 rows. So rows and columns. So we've 8 columns and 344 8 columns and 344 rows, right, of data. If we wanted to, let's say, check what was in that in an Excel environment, we could come down here and just write .csv. So the penguins is the name of the data set. If we wanted to eyeball that, we could save it over to the content folder, just to show you that folder for a moment. In the directory that comes with your Colab, the data that we use, we generally draw in from the content folder. But if you want to write out a CSV file, let's say, for instance, we want to eyeball this and see it in a traditional, classic Excel environment, then we can write the .csv penguins and give it this name. And then we can either eyeball it here. We could double click and take a look at the data set here. That mightn't be the best way to view it, but we can redimension again. If you want, we could redimension here and look at the data that's there, or might even be more straightforward. Just download the file, that CSV file, and we'll open it up. And then we can eyeball the data. It's not going to be so big. Remember, there's only 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. So we have year, we have the sex, we have the body mass, we have the species, island, bill length. Let's just redimension those so that we can see them. So species, island, bill length in millimeters, bill depth, flipper length, body mass in grams, sex, and so on. And in some instances, there are some missing data. For instance, here we have an NA that's missing. We have an NA for the sex, it's missing. And so we have a fairly complete data set, but there are a few cells where we're missing observations. Right, it's not a huge data set, so in that respect, it's not extremely. It's easy to eyeball, right, and work with. and easy to share with colleagues and so on, right? So in that sense, this is a very interesting data set. Okay, let's go back into Colab for a moment. So we wrote out the CSV file using that R prompt, and we gave that name, and it, of course, it appears here. Also in the dplyr package, right, part of the tidyverse suite, we can use the pipe operator, and that makes the code sometimes more readable. So for instance, if we just wanted to dissect or isolate the names, we could say, look, take the penguins data set, pipe operator would mean and then what are the names? What are the variables, the names of the variables? And again, they correspond to what we saw on the CSV file. If we come down and just run penguins, we get, again, another overview of what's in our data sets, something similar to what we would have seen. Now, it sets it up as a table, and that's supposed to be elegant. And if it's not fitting really nicely in terms of our ability to view here in Google Colab or in R, it will tell us, look, what you're seeing is a sample of the data. It's not the complete window. There's another 334 rows, so there's 344 in all would appear, and then we're missing 2 additional columns. So there should have been a column here for sex and another column here for year. Okay. And again, we had a look at this. Now this is ggplot2, part of the tidyverse suite as well. And one of the nice things about ggplot is that it provides us with really nice graphics, visualizations, and again, it's fairly clear something is happening. There's patterns in the data that should be useful for predicting classification of the penguin, right? And we're seeing that in the bill length and the flipper length, and we're seeing that also in the body mass and bill length here also. Now, if these are terms that are not immediately evident what they refer to, I took this artwork from, again, Allison, right, from her page. You might take again a look at that, Allison Horsts. And she has a nice graph here or image demonstrating what the bill length refers to, and then the bill depth, and also the flipper length in terms of the millimeters is this one here. Now this is a penguin from Galapagos off the coast, I think, of Ecuador, and that's a different type of penguin we're not considering. I've just included here what do we mean by the flipper, right, and its length, and that's just to give us some kind of sense of the different parts of the anatomy we're referring to in our data, right? Hopefully that makes it a little bit easier to understand. Now, in any data set, two-dimensional data set, we're talking about rows and columns. The order normally is the rows and then columns. So in matrix notation, we tend to say a 3x4 or a 10x5, and it's not clear what we're referring to. So generally, if it's a 10x4 or a 5x6, the first dimension is the rows, the second dimension is the column. And I tend to remember that by thinking of Roman Catholic, and that's that has never failed yet, just by remembering RC chimes with Roman Catholic. Okay, so we have the, if you like, well, if you're struggling with, well, what's a column? The column is the variable. So it might be, you know, we talked about the island, we talked about the species, we talked about the sex, we talked about the year. So those are the columns. And then each penguin is an observation, and it's the row, right? And again, when we run the glimpse command from, which is like the struct command, we have 344 rows and 8 columns of data. And then we get some breakdown. Is it a double? Is it an integer? Is it a factor? right? So it seems to be called the sex, the island, and the species. These are factors. And probably from the measurements, the dimensions of the penguin, we can predict which type of species of penguin we're looking at, right? So that's something that ultimately we would be interested in. Okay, so we have glimpse and we get a similar overview. Summary is also a good place to look because it's providing us with the number of Adelaide penguins, chin strapped, or 68 chin straps, 124 Gentoo. On the island, there was 106 of Biscoe, there was 168 penguins, there was 124 penguins on Dream Island, and on Torgerson Island, there was 52 penguins. And then we have, if you like, the different, the quantiles or the quartiles for the bill length in millimeters for all the population. There was 2 we didn't have records for. There's the maximum, there's the minimum, the first quartile, the minimum, median, mean, third quartile, and for each of the different for the numerical data. And then we have year and sex, and we're not, there's 2 here seem to be missing. So there's 11 penguins where we couldn't identify the sex. Okay, now we're going to use the dplyr verbs, and a good place to start is maybe take a look here at Garrett Grolemund and Hadley Wickham's GitHub, and they have a set of summary, if you like, verbs that perform actions, and there's some visuals here that might be helpful in guiding us what action is performed by a particular command. So for instance, in a very simple way, if I wanted to understand what the pipe operator did, it simplifies and makes it more readable, the code. So for instance, if we just wanted to count the number, now we have this information in our summary output, right? But if we just wanted to isolate the penguin data set and then count how many was in each species, we could perform that action. Now you can follow the visuals here also to get a sense of what the count verb does in dplyr. And if we want to do that in a way where we sorted the highest to the lowest values, again, we just very simply add sort to this command that's here, and we go from the highest to the lowest for each of the species. So the most popular penguin seems to be the Adelaide, and in fact, Adelaide was on all 3 islands. If we look here, Adelaide was here, here, and here, all 3 islands, and we can see that as well in the plots, in the facet grids. Adelaide was in all 3 islands, right? And that might account for why they're the most numerous penguin. Okay, we might like to run that same command, just changing a little bit without maybe the pipe operator. So count the data set and then the species. We might want to create a data set where we want to look at the particular species and then the island and how many Adelaide penguin were on Biscoe Island. There's 44, Adelaide and Dream 56, Adelaide and Torgerson 52, and then Chinstrap on the Dream Island there was 68, but 124 on Biscoe, right? Penguin pipe operator, so it's like saying take the penguin data set, which we've looked at in Excel in the CSV file, count the numbers by species, island, and then sort this through. So we're taking this data set here again, if you like, and we're sorting by the highest to the lowest, right? So on any individual island, Gentoo was the most numerous on Biscoe, but Adelaide penguins straddled all 3 islands. So when we add up, we get 152. right? And we could create an object if this was a data set that was important for us, for the sake of argument, or if we just wanted this data set outputted out, we could create an object. So this less than sign and then arrow, so the minus, which looks like an arrow, right? But it's just basically a less than sign and a minus. That then creates the object. And then if we wanted to retrieve that object, we could write it out as a CSV file, like what we had done before. So we could take that penguin sum and then write.csv, like what we had done before, and put it out here into the content folder, right? So if you're trying to create a table of relevant data and you want to output it, save it somewhere, that's possible to use it later on. Penguin, now the arrange verb is standard notation in the dplyr tidyverse suite. And it just basically says, look, you want to order your variables in a particular order, then use the arrange verb. And again, the syntax can be fairly simple. Take the penguin data set, use the pipe operator. So piping does what? It says data set and then arranged by the species. So we're going to, you take, it's in alphabetical order, Turgensen, sorry, the species is the Adelaide, we go with Adelaide, and then the next species, and then the one after, right? So that we order. It's not random. We're ordering the species by the name of the species. Now we can be obviously combine arrange with other verbs so that this can be a lot more nuanced, right? The filter verb is very important. When we apply it here, for instance, we might like to take a look at purely those penguins that are on the Turgetson Island. We use this operator, logical operator, to identify the equal sign means that we identify a particular characteristic in the row, and then that's the one that we want to filter. So when you're filtering, you're selecting a specific row that satisfies some criterion. Here, the criteria that we're specifying, the criterion that we're specifying is basically was the penguin based on this Turgensen Island, right? And we're getting 10 and another 42 observations or cases there. The pipe operator is combining, as we've seen, is a useful way for combining the dplyr functions. We can add a lot more nuances into our data. So for instance, if we just wanted to look at the first 10 rows in our data set, in our subsample, if you like, so arranged by the flipper length, that means, okay, we're going to take the first 10, maybe we'll take the first 20 and execute that, right? So we go down to first 20, and you can see here, we take the flipper length, and then we're going from the lowest value to a higher value to a higher value. And then we could look at the tail. And that would mean then we would go to the, if we look at the flipper length again, it's this one, we go up to 231 millimeters. So we go from 172 up to 231. And you can reverse the order here, go in descending order by using a desc command in tidyverse, and we can reverse the ordering, going from the highest to lowest. Here we go from the lowest to the highest, ascending order, but we can go from the highest to the lowest also. We see that in a moment. The filter works with different logical operators. So equal than, not equal to, less than something greater. And then the operators here that are typically used in filters, in the filter grammar, we have an explanation, right? So equal to, greater than, less than, and so on. Okay, and you can take a look at that. If we just want to look at those penguins on Dream Island, we can filter it that way. Now we could also use, so we have the double equal sign, right? Or we could layer that where we could be even more precise in terms of the criteria that we're applying. It might be we take the penguins data set and then only those penguins that are on Dream Island, and also those that have very big bills greater than 52 millimeters, right? And again, if we run that, we get a particular, we get basically just only 7 penguins that satisfy those 2 criteria. If that's something that we really needed to take a look at, we could create the object by using this less than symbol, right? So again, to write that in, it's actually just less than, and then the minus sign. You execute that, that creates an object. If that was something really important that you wanted to view out, you could post it over to here to the content folder using write.csv big bill dream. We'll give it a name, or that the object has this name, and we can write it out as big bill dreamers.csv. If we refresh our content folder, you'll see it will appear here. And again, I can download that and view it. And again, we might save it for a later period, but this might be something of relevance to a researcher, and we have the relevant information saved here, extracted, isolated, and saved in a place that we can come back to and look at again later on. Okay, so select then is used for selecting columns. So it's basically pick out, if you like, the column, not a penguin. So for instance, we might like to look at this data set purely in terms of the species, the flipper, length, millimeters, and sex. If you execute that command, we'll just get 3 columns. We've ignored the other 5. And again, we can layer that so that we can add in other verbs. So in the tidyverse grammar, we could say, okay, look, we just want the numerical values. In other words, we don't want the factors, we want the doubles and integers, and that's what gets reported out. And that we have helper functions that we can introduce with select and across. So for instance, we can, and we'll see this later on when we look at the subset data set, the smaller data sets, that these are very powerful, right? And I'll run through these again, but the select verb can be enhanced by the helper functions so that we get a much more defined set of criteria for pulling out particular columns of data. Okay, now a very powerful, and maybe I'll just mention this one, we have an across verb as well. So sometimes you want to apply a particular mathematical operation over just a few of the columns that are presented in the data set, and we want to find, okay, how many distinct observations are there for species. There was 3 different types of penguin, there was 3 different types of island, so Biscoe, Turkington, Dream, and then this was 2 sexes, but there was also NA, so that's where we're getting 3 here. The sample underscore n parentheses is it's a tidyverse verb, or the dplyr verb, and it's useful for extracting at random a particular number of observations. So if we say we want to have 10, random picks on, so pick out 10 from the 344 cases. We can do that, and then we report out here below. And we're creating an object again called penguins subset. So basically, at random, we've selected 10 cases or 10 instances of our 10 rows of data, right? And if we change, if we put in here set.seed to 40, then we can reproduce that random sampling. If we didn't include this in, then each time we run this bit of code, we're going to get a different 10 cases. So if I run this again, I'm going to get the same. But if I remove this line of code here, each time we can do that. Let's run that. Okay, you can see 50.8, 15.7. If I run that again, something different, something different, something different. But if I set the seed, I can always reproduce that random choice, right? So when I run it, it's always the same. Notice I'm getting the 49.1, always the same. Okay, so let's come down then, and if we glimpse, we can take a look again at our data set. We have 10 rows, 8 columns in this instance. And that's, again, a subset generated from here. And because it's easier to view with the smaller data set, I'm going to use the penguin subset just to demonstrate a little bit more what happens when we apply the arrange verb and select and filter and so on. So for instance, before when I ran arrange, we could only see the Lee, but we didn't get as far as chinstrap or gentoo. We can see here when we apply arrange species, it means order the variables by their species. So we start in alphabetical, we go in alphabetical order, right? And if we run the same again, then we reverse the order. So now it's, we start with the G, C, and then back to A. So we're reversing the alphabetical ordering, right? Arrange descend is a useful way for ordering our values. Sometimes we want to go from the highest to lowest. Sometimes we want to go from the lowest to the highest. So if we use desc, so arrange the penguins subset, and we apply this arrange desc bill length bill length you can see we're going from the highest to the lowest. We're going in descending order, right? Descending order here in our data set. Okay, we can filter the subset using these criteria. We saw that before, so I might take my penguin subset and apply filter. And we're getting more, we're saying basically the penguins that have bill length in excess of 44, and there's only 1, 2, 3, 4, 5, 6 that satisfy that criterion, right? And we could do bill length greater than, or bill depth greater than 18.1, and it was only 3. So bill depth, all of these are greater than 18.1, and it was only 3. Okay, and again, we could be very finicky. Okay, only the elderly species and the bird we're looking for must have a bill length in excess of 40 millimeters, right? And there was only 2 birds that satisfy both. So elderly species and the bill length bill length greater than 40. So only 2 out of the 10. The logical operators that we use for filter are the following, and to understand a little bit these operators, if for instance we took the penguin subset, we said, look, we want the chinstrap species and the gentoo species, that would be both, right? So we're saying we must have gentoo, and chinstrap in our data set. That's all we want. We must satisfy this criterion. So the species must be this or this. So we're getting that union, if you like. And then we can use the in command as another way of doing the same. So the species in and C, right? So I should put here, and then we would have C followed by C, right? So C open bracket, close bracket, and then you would set out whatever the species had to be equal to. So the chinstrap and the gentoo. Again, we could perform the same activity. So we could say filter chinstrap and species, so or we could use this command, the in command in tidyverse, and we get the same output. Or we could have just excluded not equal to. Exclamation equal means not equal to. So in each instance, we're getting the same output for those three commands, right? And again, you can follow up a little bit. I've left the hyperlinks, and you can follow back to the cheat sheets, right, to view some of this syntax. Slice also is quite powerful. So the first three rows, right? So slice penguins, that's Dataset, and then subset, and just take the first three rows. The top tree by body mass. So the bigger penguins are presented. We can do filter and select together, and that can be quite a powerful way of layering or setting out the context of what we want to achieve. So body mass less than 3,500 grams. Penguin subset, select year, island, and species. And again, you can see here that the select and filter present us with ways to very much target. If we have species to body, so the columns between species and body, mass by grams, body mass G, right, are included in the data set, but we don't have year. So anything between those two columns is included in. And then we might want to select our column that has satisfied some criterion, like select starts with bill, and there was two, bill length and bill depth, right? So the starts with is a way of finding those columns that have this particular wording, ends with millimeters. So only those columns, there's three that end, there was three columns that ended in contains the word length. So bill length, flipper length, and you can see we identify those two columns. And again, that's quite a significant way. We can imagine going through a business data set or a HR data set, and we're looking for a specific name. So it might be Tom, or it might be James, or it might be a product. There might be three different types of products that are water based or have some mechanical property, and you can identify that just using that command. And so that opens up a lot of avenues for investigating your data set. If you want to exclude a variable, just say select and then remove the negative island. So again, we identify the data set, use the pipe operator, and then everything in there except island. So island is missing. Select contains length, starts with bill, right? So here we're being very nuanced, contains length and starts with bill. And now there's bill and flipper length and bill depth. So we have contains length or starts with Bill. Right, so we're getting a union of all those constituent bits that contain length in the title of the attribute, and then the starts with Bill. Penguin, here we combine filter and select verbs together. So we're filtering for the Adelie species. The bill length must be greater than 40. And we only want the species sex and the bill length M reported out, right? So in a very targeted way, we're taking the 10 observations, 10 rows, 8 columns, and we're filtering. So we just want those birds of the 10, those that are Adelie, have a bill length more than 40 millimeters. And then we only want information relating to their species, to their sex, and bill length. Okay, and again, that's a very targeted way of, by filtering and selecting, we can really transform our data, summarize our data, and provide report out to relevant parties. Again, using the pipe operator, we say the data set, and we're filtering so that it's less than 45 millimeters, the bill length. And then we want to report out the species, the sex, and bill length. Here we done the same again. I think, is that the same? It's the same bill length. Yeah, it's the same again. Okay, 5 by 3. That was 6 by 3, less than 45, less than 40. Oh, and we also specify the species must be Adelie. So that's even more restrictive, and that's why we lose 1 down here, right? We don't want the GAN2, we just want the Adelie that satisfy the other criterion. Okay, we might want that the sex is not female, that would mean male or NA, and the species must be Adelie, and we have a bill length less than 45, and we only want to report out the species, sex, and bill length in MM, and that's what we get, right? If we filter the bill length and we're going between the range 16.2 to 18.1, right? Again, it's providing boundaries, a window within which we only want those particular. Again, if we were considering sales or commission to a sales rep, and we want to identify a particular group of sales reps that satisfy or in a particular category, numeric category, it's easy to identify at that particular grouping. And again, that's what's making data transformation so useful to users. Of course, we can do a lot of this in Excel, but it's just a little bit more finicky and requires a lot more attention and involves a greater number of steps. So data transformation is a very powerful way of identifying with specific criteria what it is we want to filter out or select out of our data set and apply it. We also have the in command, C, open brackets, close brackets. And we're using this again on our subset data. And you can see here, we're filtering so that we're just pulling out the Dream and Bisco, and then select species, sex, bill length. So out of there's only one of the birds on Turkenson. If we go back to the original data set, the penguin subset. So let's come back down here. Right, if we, yeah, when we're just looking at it, so the full subset would be if we went percentage or, and then looked at penguins subset. And look at the full 10 observations here. You can see we had one for Turgensen, right? So when we look at the island one here, this number 3 here was Turgensen. Now we've excluded that by just selecting these two, and we don't have that Adderley Turgensen with a bill length of 40.6 because bill length of 42.5. That 42.5 doesn't appear here because we've excluded. Okay, so other subset verbs for columns in use that are available. You might take a look here at the hyperlink. That'll bring you to the cheat sheet, right? And they can also be applied. Mutate is also a powerful way of estimating a new column. So for instance, mutate computes and appends a new column to the existing data set. So for instance, if we wanted to add in the body mass in terms of kilograms, if we divide the column, each observation in the body mass G by 1000, we convert to kilograms. And you can see here, when we run then our estimation, we're getting the regular columns for species, sex, and body mass G, but we're also getting the body mass kg. So mutate creates a new column. We can perform a mathematical operation on an existing column or a combination of existing columns, and then when we print out, we get that as an additional column to our data set, which is different to transmute. Again, here we convert it to pounds, right? And we ran the full, in this instance, we didn't limit by selecting, we took the full subset again, but now we have the body weight in pounds, which would appear here, would be the last column in our data set. We've done that again, but we've just said, look, just report out species, sex, body weight in pounds. And here we have the pound weights for the 10 birds. Okay. Bill ratio is the bill length divided by bill depth. And again, we can do the same. So mutate basically has this property of you can create some combination of existing columns using a mathematical operation. And then when you report out your data set, you have a new column created in that existing data set. Transmute is a bit different because you compute one or more new columns, drop original columns. Transmute is a function that mutates columns and returns only those columns, right? So for instance, if we transmute, if we perform that action again, we only get the new column, right? If we're converting to pounds, right? So transmute penguin is equal to species, island, and body mass. You can see we are creating, we're saying, look, we want to report out the species, the island, and the body mass in terms of kg, and we have this mathematical operation, right? Again, we've done the same. Now I've created an object here. I've written it out as bmkg. And then when I apply, if I just run bmkg, this is what comes out. So that's the name of the data frame, and this is the name of the column, right? And I could rename it, and that's also a powerful feature. We could rename our body mass kg to be bmk. right? So rename also is from time to time, you need to update columns to reflect maybe change in the product name or change in a process, but we need to take existing data and reclassify or rename it, right? The summarize function aggregates the data. Maybe we take a number, a large column of information, a number of columns or data points, and we summarize that or aggregate it. So it creates a new data frame. It will have one or more rows for each combination of grouping variables. Below it would appear that we do need to remove missing values. So for instance, if I run this report, penguin, and then summarize the data, create an object called the average body mass by taking the mean of the column modi bas g, we get an NA, but that's because there's a number of those cells missing. And if we remove the NA, then if we do the same syntax as before, apply the same syntax as before, but add in the condition and remove the NAs, we now have an average of 4,202 for the average body mass in grams. Okay, and we can summarize again, get the standard deviation. So we have these mathematical functions, the minimum, maximum, mean, median, variance, standard deviation. Here we estimate same syntax as before, but now it's SD, so standard deviation. The variance, and if I take the square root, if I just take the 600 and so the variance of the body mass was 643,131. If I take the square root, that brings me back to 801, almost 802, 801.95. So that's why the standard deviation, we're getting the rounding here. Okay, and distinct, useful, how many different types of species? There was 3, and we can summarize that, or we could use the count. We could use a cross. So for instance, we counted long beak and then the bill length in excess of 50 meters. And there's 290 that don't have bill length in excess of 50 meters, but it is true in 52 cases, this condition is true. We satisfy this condition. And then 2, we have NA. And then a cross allows us to perform a particular mathematical operation, but across a number of different categories. So if we were to summarize and get that N distinct, how many categories, how many types of particular species were there, unique species? So when we look at distinct, we're looking at how many unique features, how many different types of species. So across species, so summarize across species that were distinct, it was 3 of each. But if we leave out our, so if we exclude, so the exclamation mark here means exclude these 3, then we're just left with, there was 165 distinct bill lengths, millimeters, bill depths in millimeters, flipper lengths, millimeters. There's 56 separate, 95 unique, and there's 3 unique or separate years, distinct years, right? And again, do it across everything, meaning everything. Again, this is very self-explanatory. Then for all of the variables, right? For all of the columns, right? Pivot tables are hugely important for summarizing and presenting relevant information. And we can accomplish that by using summarise and group by. So group by takes an existing table and converts it to a grouped table where operations performed by group. So for instance, we may wish to take the penguin dataset. So this is the full sample dataset. Apply the pipe operator. So and then group by species. So break it down by the different types of penguin, Adelie, chinstrap, and gentoo, and then summarize each so that we get the average body mass. We will remove the NAs, and we refer to it as the average species body mass. So we get the average body mass for Adelie, the chinstrap, and the gentoo. The gentoo looks completely different in terms of body mass compared to the other two. So we can distinguish gentoo, it would appear, by the body mass typically from the others. Seems to be distinctive in body mass, seems to be much bigger. Okay, other types of reports we can apply. So penguin, group by species, and summarize, get the mean, but we might like to also get some data relating to the standard deviation. Then we have, okay, we're grouping by species, and we get the Adelie, chinstrap, and gentoo, and then we're getting the average body weight, and we're getting the standard deviation. Now, if we wanted to change that to island, group by differently, let's say the island, and run that report again, then we get the average body weight by the island. It doesn't seem to be the Bisco Island seems to have bigger it seems to have bigger birds, but then there's a disproportionate amount of gentoo on the Bisco Island, and so that's why we're getting that higher figure. And we could do it maybe by year. So we put in year, and in 2007, the average body mass was 4,125 grams, 4,267 for 2008, 2009, that's 4,210. So not a huge amount of variation. Maybe there was more food available, and the standard deviation is roughly the same. And I would say the mean, it hasn't differed that much. But if that becomes more meaningful, so the animals are not getting bigger or really smaller noticeably, well, they are getting a little bit bigger through time. Is that a natural progression, or was it a bumper year for fish? That's an interesting scientific question. We're not going to be able to answer it here. We can go back to species, run that again, and we get that pivot table out. So this is a very powerful way of presenting the data. And again, doing this in Excel without these type of tools would present some degree of difficulty, perhaps, particularly if we layer it with more and more mathematical operations. If we limit it to 2 in Excel, that would be fine. I think as we increase the dimensions of our table, then that becomes a little bit more difficult in Excel. And that's why data transformation tools in dplyr is really useful. Again, here we're going to take the penguin dataset, the full dataset, we'll group by the species and the island, and then we'll summarize by taking the average. So basically what we're doing here is we're taking another categorization. And so we now went from 3 to 5. Not the chinstrap are only on Dream Island, and the gentoo are only on Bisco Island. Adelie was on all 3 islands. So, and we're getting the average weight of the Bisco in the Adelie species in Bisco, Adelie species in Dream, Adelie species in Turkington, and they look very close. Not a huge amount of difference. Chinstrap, bit bigger, I would say, but not much. And then the Gen 2 is significantly bigger. We could put in year here to add in extra dimension. Now, as you increase the dimensions, your table becomes a little bit less intelligible, but you can see how we expand it out. So the Adelie bird on Biscoe Island in 2007, on average, its body mass was 3,620. And then in 2008, it went up to 3,628. And then in 2009, it went up to 3,858. Now that's a bit of a jump there. So what we could put that down to, maybe there is something going on. Maybe there's more fish. Maybe there's less competition with other animals. We don't know. Again, that's a scientific question, but at least we can present the data and perhaps we can find interesting questions. Adelie Dream, 2007, 8, 9. There's an increase and then a decrease. And on Turgensen, there's an increase, decrease. And the Chinstrap and Dream, there's an increase, a decrease. And the Gen 2 and Biscoe, a decrease and then a substantial increase. So a decrease first and then a substantial going through time. Again, because we have these factors, because we can describe our variables in terms of as factors, we can isolate them and then we can add more. Of course, we could put in standard deviation, but we can make this pivot tabling quite useful and get reports that are meaningful to scientists. Okay, so again, we can group by species, island, and sex. Again, we could have put that here, maybe add in sex here and run that report. And you can see we get, okay, now it's become quite significant. We can output that as, to write it out as an object. And you can see we can get more layered type of labeling for different species, island, year, and sex. And if needs be, we could write that out to, as a CSV file. Down here, we have broken up species, island, and sex. And you can see the output that we get here. So on average, the female is smaller than the male. Female 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 smaller than the male for that characterization. The NA is, in some cases, it wasn't clear what the sex of the penguin was, right? Okay, so that's pivot tabling, and it's a powerful way of creating reports, writing out reports, communicating your data set, where we aggregate the data and summarize. And again, it's might be useful to think about what it is. When we summarize, we're taking a number of data points and then expressing it in terms of a mean or a standard deviation or a median. And then we can do it for a particular categorization. And that's where the pivot tabling comes in. So we want this mean for the sex, filtered out, for the island, for the species, and so on, right? And so we get these very rich reports that can be created, that have some kind of meaningfulness, that may also then prompt additional research type questions. Are the animals growing over time? Was there food shortage? Are there resource issues for these animals? Is the body weight falling? Are the animals stressed, and so on? And again, that's something that we're able to perform here. These type of questions can be set up, and we can get some kind of sense of key trends and so on in terms of creating those pivot tables. Okay, I'm going to leave it there.